All right, folks. Welcome back. We are going into the second half of 4-6. We just got done solving rational equations. Now we're going to look at solving rational inequalities. All right, what's this going to look like? I'm going to dive in because we're just going to use examples to kind of investigate what happens with this type of problem. Now, the first thing that I have to warn you is when you're doing these problems, especially like on a quiz where they're all mixed together, you have to kind of stop and analyze what type of problem do I have? Like before, when you see an equal sign, you'd say, I have a rational equation. With a rational equation, I solve by finding the least common multiple and so on. You go through your strategies. When you see this, when you see an inequality, the strategy changes because think of what we do with inequalities. Just like when we solved absolute value inequalities, we were solving for kind of boundaries of our solutions, right? You're going to have infinitely many solutions because this is simply greater than one or less than something or something of that sort. So you're looking at a much different solution set when you're done. It's not going to be a single number. It's going to be a region. It's going to have boundaries. So that's going to be kind of the approach we look for. It's going to look similar in some parts to solving, but it's going to be for a different purpose. So I want you to pay close attention to what we do here. All right, first, when we look at this, we see it is a rational inequality. The first thing I want to do, my first step, is I want to make sure I find where the denominator equals 0. Because any value, if I have a denominator that has a variable in it, I've got to see, is there any way my denominator becomes undefined? In this case, b equals 0 would be a problem, right? So right off the bat, with an inequality, we are going to start defining some kind of limits or borders. All right, the way I do this, the easiest way I know to teach you this is before I do anything else, I make a number line. All right, and on that number line, I just start looking at where my boundaries are. I know b cannot equal 0. For any reason, it cannot equal 0. So just like we did before when we had a boundary on a graph, if it was we were graphing an inequality, we did it as a dotted line or dashed line so that we said it cannot include this boundary. The same thing here. There's no way b could be a solution here. So we are going to eliminate b by putting a line here. So now we've kind of divided space into two regions. We might have answers on this side or on this side. So again, we're looking at that idea of boundaries. We have one boundary. We find the next set of boundaries. All right, now the next step is our boundaries. And we do that using the equation that models this inequality. When I say that, what I'm saying is I'm going to look at 1 over 3b minus 2 over 5b less than 1. And I'm going to solve this instead by getting rid of this and just saying equals. So if you like what we did before, this is part of what we did before, right? Now I'm going to approach this just as an equation, but I want to be really clear. What we're looking for here is boundaries. We are not looking for solutions. These do not tell us solutions. That's why I want you to change it to equals. So you understand we're just finding the endpoints of different solution regions. All right. So least common multiple here looks like 15b. So I am going to multiply by 15b. And when I do that, I'm thinking of it as 3 times 5 times b. The 3 and the b would cancel here, leaving me 5 times the 1 that's there. Minus here, the 5 and the b cancel, leaving me 3 times 2, or 6. And equals 15b times this. That would be 15b here. So 5 minus 6 is -1. Equals 15b, divide by 15. And what do we end up with? We end up with a -1/15 equals b. So that is a boundary. We go back up to our number line and we put in -1/15. So I'm going to put it over here somewhere. -1/15 is a boundary. And I did it as a dotted line again because I'm looking at this now. This is strictly less than, and so I have to not include the boundary that would make this equal to. If this was less than or equal to, then I would make this a solid line, which would include that boundary. All right, but in this case, we have that. So now we have all our boundaries. We've looked at the boundaries created by where the denominator is undefined, and we've also looked at the solution boundaries of the equation. So we have three regions here. All right, and these three regions can be described pretty easily. We have, and this is what I'm going to do next, is I'm going to list those regions. The first region is from negative infinity to negative 1/15. The second region is from negative 1/15 to 0. And finally, the third region is from 0 to positive infinity. All right, now, again, those were these three regions up here, right? The first, second, third region. What I'm going to do now is go back to my original inequality, that one that says 1 over 3b minus 2 over 5b is less than 1. And I am going to test each one of these. So that's our next step, is to test each of these regions to see, does it work? Remember when we graphed equations or inequalities on a coordinate grid, we drew the boundary line. And once we had our boundary lines, we tested a point. Same idea here. We're just going to test an x value, in this case, a b value. So between negative infinity and negative 1/15, I would say b equals negative 1 would be a good test. That would be in that region. And I would plug it in. So 1 over, when I do negative 1 times 3, I get negative 3 minus 2 over 5 times negative 1. So that's a negative 5 less than 1. So negative 1/3, and this becomes plus 2/5 less than 1. Well, is that true? Is negative 1/3 plus 2/5 less than 1? Well, let's look at this. If we do these as 15ths, right, this would be negative 5/15 plus 6/15 and greater than 1 is what we're trying to see. Negative 1/15 plus 6/15 is a positive 1/15. That is not greater than 1, right? That is less than 1. So this is a true statement. That means this is part of our solution. All right, 1/15 less than 1 was true. We go on. All right, so now we go to the next one. Between negative 1/15 and 0. I'm going to pick something that works out nicely. I'll say negative 1/30 would be between there, right? It's smaller, and 30 has nice divisors with this. So I'm going to say b equals negative 1/30 and put that in here. So that would be 1 over 3 times negative 1/30 is a negative 3/30, which is a negative 1/10, minus 2 over 5 times this would be a negative 5/30, which is a negative 1/6. And we want to see, is that less than 1? So 1 over negative 1/10 is a negative 10, right? And minus a negative 2 over 1/6. Well, 2 over 1/6, we'd flip and multiply, and we would get 12, right? So that's plus 12, right? Because we'd flip this, and it would be 2 times 6, 12 over negative 1. So that makes minus the negative 12 is plus 12. Less than 1. Is that true? Well, negative 10 plus 12 is 2. That is not less than 1. So that is not one of our solutions. We keep moving. 0 to infinity. I'm going to say b equals 1. So 1/3 minus 2 over 5, right? Multiplying each of these, putting b equals 1 in, less than 1. So again, in 15ths, this would be 5/15 minus 6/15 less than 1. And that is what, negative 1/15 less than 1. Is that true? Sure. So that is another one of our solutions. So our final answer would be, in the answer blank, we would have negative infinity to negative 1/15. And we would have from, what was the last one? 0 to infinity, I think. Yeah. 0 to infinity. And you could put a union symbol in between them, but it's those two regions. All right, so that's one example. I'm going to give you a couple more, guys. It's going to take us a couple minutes, but I want to show you the different ways this can manifest itself. So that was one of our problems. Now, let's go to another one. Let's do this one. Let's go with this, for example. 5 plus 1 over x greater than or equal to 16 over x. So again, the first thing I want to do is I realize this is an inequality, so I'm making a number line. All right, values that cannot be in my denominator. 0 again. So 0, I leave out, and it's a dotted line because there's no way 0 can be an answer for this, so I can't include that in any solution. And then we go on. Next step is to look at 5 plus 1 over x equals 16 over x. And it would appear that our least common multiple here is x. So we would have 5x plus, I'm sorry, I said it, didn't write it, 5x plus 1 equals 16. So 5x equals, let's see, what is that going to be? 15. And x equals, when we divide by 5, x equals 3. So at 3, I have another boundary. Now remember, I look now to see for, do I include that boundary? This was the solution, so I am including it because this was greater than or equal to. So I'm going to make a solid line here. And again, I have 3 regions, it looks like. And I'm going to describe those regions. First region is from negative infinity to 0. Second region is from 0, and 3 is included, right? I just wanted to double check that. To 3, we make a bracket there, right? Because we're including 3. And then our third region is from 3, including 3, up to positive infinity, right? Just going forever. And so we would write out those 3 areas. And again, I usually, as I'm working down, I like to have it right there where I can see it. I'm going to write 5 plus 1 over x greater than or equal to 16 over x. And so I'm going to use this to fill in the blanks here. So now I'm going to pick x equal to between negative infinity and 0. I'm going to say negative 1 again. So I'd have 5 plus 1 over negative 1 greater than or equal to 16 over negative 1. So that is 5 minus 1 greater than or equal to negative 16. 5 minus 1 is 4 greater than or equal to negative 16. And that is true. So I have this. That's part of my solution. Now I go to the next one. Now I've got x equal to, say, 1. All right, if I do 1, I get 5 plus 1 greater than or equal to 16. So 6 greater than or equal to 16, that is not true. That is not part of my solution. Here, we have x equals maybe 4, right? If x equals 4, we would have 5 plus 1 over 4 greater than or equal to 16 over 4. So 5 and 1/4 greater than or equal to 4. That is true. And we have our solution. The solution would be negative infinity, 0, and whoops, I made the wrong symbol there, sorry. And from 3, inclusive of 3, to positive infinity. That is our answer. All right, one last one. And this one I just want to show you because I want to show you a trick. If you ever get, sometimes they give you these problems, 2 things about them. Sometimes they give them to you in factored form. And I would leave them in that form. And then also sometimes they're comparing them to 0, saying greater than 0 or less than 0. And I'm going to show you what we can do with these. All right, so first thing, I see this as an inequality. It's a rational inequality because we've got a rational expression being compared to something else. So I'm going to make my number line. And number line went a little crooked. Let me do it again. Try to get it straight. There we go. All right, so we've got our number line. Now, what's going to make the denominators of each side equal to 0? Well, it looks like 1 and -1. So I'm going to have at 1 and -1, I'm going to have, what are they going to be? They got to be dotted lines, right? Because we're not including them. And then we have to solve this. Well, when we look at where is this going to be equal to 0, this one is kind of, I don't even have to write it down. If I'm looking where x plus 2, I'm going to write it down, even though I said I don't have to, because I want you to see what I'm doing. If I'm doing this, where is this equal to 0? Isn't that just going to be where this is equal to 0? Because if this is equal to 0, the entire fraction will be equal to 0. So where is that going to be equal to 0? That's going to be equal to 0 when x equals -2 or x equals 3. So I'm going to add those in here. I'm going to have -2. And again, I look up here, that's going to be a dotted line because it's strictly greater than. And then I'm going to go to 3. And we're going to have another dotted line. So fun, fun, fun. We have 1, 2, 3, 4, 5 different regions to investigate. So let's do this. Let's write them out. First one is going to be from -infinity to -2. The second one is going to be from -2 to -1. The third one is going to be from -1 to +1. And the fourth one is going to be from 1 to 3. And finally, the fifth region is from 3 to +infinity. And we are going to use where, what do we have? X, well, it's going to be this thing, but instead of this, it'll be greater than 0, right? So we try to find if this is going to be greater than 0. This is easier than it looks with this one, because say I pick, say, x equals -3. What I can do is just look at this and look at each number. If I put -3 in x plus 2, that's -3 plus 2, that's -1. So it'd be -1. I put -3 in here, it would be -6. I put -3 in here, it would be -4. And -3 in here would be -2. So what do we end up with here? Well, we get, what I look is real simply, this is a positive over a positive. So it's going to be positive. Isn't that what it's asking? Is it greater than 0? Yes, it is. It's greater than 0. So we can even shortcut this a little more. If I say x equals -1.5 here, because that's between -1 and -2. If I put -1.5 in here plus 2, that's going to be a positive number, right? -1.5 minus 3 is a negative number over -1.5 minus 1, that's a negative number. -1.5 plus 1 is a negative number. So for this one, I'm going to have a negative over a positive. Overall, that means negative, right? So this will be, or will not be, I'm sorry, just did that mistakenly. This will not be greater than 0, right? Because it's going to be a negative number. Negative over a positive makes a negative. I don't even really care what the numbers are. It's just negative over positive. That's not negative, so that doesn't work. The next one, I've got -1 to 1. So let's say x equals 0. Well, if x is 0, I got a positive, a negative, and a positive. So I'm going to have, this is going to be a, let's see, well, let's do it down here. This is going to be a negative over a negative. That makes a positive. That is greater than 0, right? So that one works. Between 1 and 3, x equals 2. If x equals 2, 2 plus 2 is +4. 2 minus 3 is -1. 2 minus 1 is +1. 2 plus 1 is positive 3. So we've got a negative over a positive. That makes a negative that is not greater than 0. Between 3 and infinity, I say x equals 4. 4 plus 2 is a positive 6. 4 minus 3 is a positive 1. 4 minus 1 is a positive 3. And 4 plus 1 is a positive. So we get positive over positive, and that is greater than 0. So that one is part of our solution. And we would write those 3 down. So we would have from negative infinity to negative 2, and from negative 1 to 1, and from 3 to positive infinity. So I kind of like those ones where they give me the factored form and compare it to 0. I think it makes life easier. So different approaches, or same approach, different problems, some different little kind of strategies and tricks in there. But remember, in general, what you're going to do is you're finding the endpoints of those regions. You got to recognize immediately that you're dealing with an inequality. So we're going to have boundaries, not solutions. All right. So that's what we're looking at, guys. Until I do 4-7, I will see you later. We're going to do 4-7 next. Have a great day.